Okay, so what I want to do in this online lecture is review the things that we did in class the last time we met and talk a little bit more about this special distribution that we call the normal curve, and in particular the special distribution, which is the standardized normals curve that we get when we look at the distribution of z values. The last time we met, we talked about how a distribution that looks like this is called a bell-shaped curve or a normal distribution. Sometimes you might, and we won't use the terminology, but you might have also heard it being called a Gaussian before, so that's like the technical term for it as well. And when we look at a distribution like this, an entire distribution like this can be described by just two numbers, the mean and the standard deviation, where this number here is the mean, so the number that actually happens to be the peak is the mean of a normal distribution, and a standard deviation is the value where about 68% of the area under this curve falls within one standard deviation of the mean. And we didn't actually talk about how you can kind of visually know that one goes here and here. How do I know that it's not, if this is 0, how do I know that I'm not putting one standard deviation, -1 here and +1 here? So, right, I'm saying that one standard deviation below the mean is down here, and one standard deviation above the mean is up here and not there. And visually, the way that you can kind of just guess, kind of do a ballpark, there's a few homework problems that have you looking at a Gaussian or a normal distribution and figuring out which curve looks like something has the means and standard deviations plotted in the right spot. And one standard deviation away from the mean will be a bit more than half as tall as the overall curve. So it's about, I think it's 62 or 63% as tall. So this height, if you carried this over to whatever the y-axis was, which would probably be a relative frequency, this height here of the value of this normal distribution at one standard deviation above and one standard deviation below, you carry that over, would be about 2/3 or so as tall as the peak itself. So that's just a kind of quick way to judge where to draw these one standard deviation above and below the mean. Okay, so the example that we did in class was we said, what is the value of z less than or equal to 1.23? And I want to redo that just so that we can remember how to use these tables. This is a plot of the z, and so remember that z has a mean of 0, that's why the mean of this distribution is here, and a standard deviation of 1. So a value of z equals 1 is a value that is 1 standard deviation above the mean. A value of z equals 2 is 2 standard deviations above the mean, and etc. So a value of z is 1.23. That'll be somewhere around in here. There, z is 1.23. So it's sort of around in there. And if we want to find the probability that z is less than or equal to 1.23, what we are looking for is the probability that we are in this region of the graph. So all the z values that have numbers that are less than 1.23 fall to the left of this number here. And so if I randomly picked a z value, the chances that that z value that I picked would be one of these numbers that's 1.23 or less would be the area under this curve. So to figure out z values, we use this table here. And so this table has in the first column the first two decimal places of z. I should say, sorry, the ones place and the first decimal place of z. And over here on the top row, it tells you the second decimal place in z. So if I am looking for z is 1.23, if I can zoom in and have it not ruin everything else. Zoom in a little bit. So I am looking at the row of 1.2, and here are all of the digits that are 1.2 something in my table. And I want to find 1.2, and then I'm going to go here and find the 3. I'm going to follow that down, and I find 0.8907. Okay, so I found that that is 0.8907. So the area under this entire curve is 1, and the area to the left of 1.23 is 8.8907. So the probability that any z value that we were to randomly select was less than or equal to 1.23 is 89.07%, or just 0.8907 in decimal form. The probability that the z value that we picked, if we picked a z value greater than 1.23, now we are looking for the area under the curve down here. So if I randomly picked out a z value, used, say, simple random sampling to just randomly select a number, and I picked a z value, there is, however big this area under the curve is, of a chance that it is a number greater than 1.23. The area under the entire curve is 1, and the area under this portion of the curve is 0.8907. So the area to the right of the curve is 1 minus 0.8907. And that gives me 0.1093. So there's about 11% chance that a random z value, if picked, would be greater than 1.23, and about an 89% chance that it would be less than that number. So when we read numbers off of the normal table, these tables, we are always reading for numbers to the left of the digit. So if z is here, the z value that we find in this table tells us the area of the shading to the left of that number. And that's what we're always getting from this table. All right, so that's enough review, I think. Let's do a new version of the same problem. So I said in the last problem, what if we have a normally distributed data and we want to figure out what is the probability that a certain z value is what we have picked. But we can also flip that around. So sometimes, instead of what we just did, what we want to do is start with the area under the curve, and we want to find the corresponding z value. So as an example of this, which z-score represents the first quartile in a normal mode? So the first quartile, Q1, is the 25th percentile. This is the number that divides the bottom 25% of the data from the top 75% of the data. So equivalent to asking what is the value, what's the z-score represents the first quartile, what we are looking for is where can we, what z value on here makes it so that if we shade the area to the left of the curve, we get that the area under the curve is 0.25. So we're going to go back to our same table, only now we are looking for a probability of 0.25. So I'm going to scan through this table and look for something that starts with 0.25. And I see that I start at 0.5, and then we they sort of go up and up and up and up and up and up, and all of the numbers on this table are bigger than 0.25. And that, if you think about it, should make sense because all of these z values here are positive numbers. So that's a way of saying that z greater than 0 is always greater than a half. When you're in the right-hand side of this curve, there's always at least half of the curve remaining. So in order to look at this, we're going to flip it over and look at the negative z values. So now this is the same table, only now we're looking at values of z that are negative. So what we're going to scan through here is look for portions of the curve where we find about 25%. So I'm looking for the number 0.25 somewhere in this table. And I've already circled it. Where I see it in this data is right here. So I see two numbers here that straddle 0.25. Neither of them are exactly 0.25 in this table, but I have 0.2514 and 0.2483. So somewhere between these two z values is my first quartile, is where 25% of the data is. So let's write that down. 0.25. And let's actually go back to this. Figure out exactly what z-score corresponds to 0.2514. So if I travel this over to the left, I find that it's negative 0.6, and then I travel up, I find that it's 0.7. So the z value that corresponds to 0.2514 is negative 0.67. So let's write that down. Now if I go do the same thing for this other value, here's my 0.2483, and the z value that corresponds to 0.2483 is negative 0.6, and then I follow this up to the top, and that's 0.8. So negative 0.68 is the other z value. So the actual z value that corresponds to the 25th percentile is going to be between these two numbers. But with this table, we can only do these 4 decimal places. So this is as good as we can do. So in my homework, I'm going to write down the one of these that is the closest to 0.25. This one is 14 and this one is 17 away. So we'll pick this one. And in my homework, I will write z is negative 0.67. Okay, so the z-score of negative 0.67, that's on this line, somewhere between 0 and negative 1, greater than half, right about here. The z-score of negative 0.67 corresponds to the first quartile. So 25% of all of the possible data choices will be have a z-score of less than or equal to negative 0.67. Okay. So here's a few more. And if you're doing this on your own and watching this on your own, I would highly recommend pausing this now and trying to do it on your own and figuring and then checking this video in the end to see if you got it right. Okay, so I'm looking for the area to the left of z is 0.2119. And when I go through here, now because z is less than a half, I know I'm going to be looking on the negative side of the z table because all of the z values less than a half are negative z's and all the values greater than a half are positive z's. So let's look on the negative side of the table, and I'm looking for 0.2119. So I find 0.2119 right there. So the z-score that corresponds to 0.2119 is negative 0.80. And that is saying that for a z-score of negative 0.8, so here's a z of 0, and I'm kind of looking for the spot where the peak drops down to about 2/3 of its maximum, and that's where I'm going to draw my plus or minus 1 standard deviation. So that's where I'll do my 1 and my -1. So a z-score of negative 0.8, that falls right about there between 0 and -1, and 21% of the data is to the left of that z-score. Okay, the area to the left of z is 0.9948. So it's a number greater than a half, so I'm going to flip it over to the positive side of my chart, and I'm looking for 0.9948, and 0.9948 is right here. So I'm going to follow this over to 2.5, and then I can follow this up and find that that's 2.56. So that is a z is 2.56. So if you draw this, a z value of 2.56, that's 2.5 standard deviations above the mean. If you remember from the empirical rule, 95% of the data is within 2 standard deviations of the mean. So this is a really large z value. It's an unusually high z-score. And that fits with what this z-score is. It says that 99.5% of the data is to the left of this score. So again, with my 0 and -1 and 1, 2, 3, here's 2.56. It says that this tiny little sliver of the curve, the area of that tiny little thing, is about 0.5%, and the area of everything else is 99.5% of the curve. The area to the right of z is 0.05. So now we are looking to find a normal distribution where we want the area to the right of it to be 5% of the area. So we're actually looking for a spot where we're only going to have 5% of the data shaded. So if I'm looking at this curve, if I'm all the way over here, then the area to the right of that is going to be a really big number. I want to find the area to be a really small number, so I'm going to guess that probably I'm looking somewhere around in here, right? That sort of visually to me looks like maybe that's about 5% of the area under the curve right there, and then that leaves 95% to be the rest in there. When we look up the z values, it doesn't tell us the area to the right of the curve. It tells us the area to the left of the curve. So if we are interested in finding something that is to the right, what we need to do is we'll figure out the area to the left with this table, and then we can subtract that from 1. So if this is 5% of the data, that means that leaves 95% of the data to the left. So we are looking in the table for z is 0.95, because that 95% of the data is to the left if 5% of the data is to the right. So I'm going to search in my table for 0.95, and I come over here and I see these two values right here that straddle 95%. So 0.9495 and 0.9505. They are both 1.6, so z is 1.6, 4, or 5. So this is z equals 1.6, 4, and z equals 1.65. So in the last example that we did like this, where the z value was between the two numbers, there was one number that was closer to to the number we were looking for. Here, both of these are equally far away from 0.95. So you can pick either z-value. You can pick 1.64 or 1.65. The true z-value looks to be probably pretty close to halfway between the two of them. So in your homework or on a test, your homework would accept either of these as the answer. Okay, this last one is tricky. So we're looking for something that says the area between z and negative z is 0.903. I think you really have to think hard about normal distributions in order to feel good doing this one. So let's draw a standardized normal distribution of z. 0, 1, 2. Okay, so there's a standardized, that's the distribution of z. And we are looking for this. Between z and negative z is about 90% of the data. So we're looking for some sort of a z-value where 10% of the data is out in these tails. Or I guess a little bit less than 10%. I'm just going to round this to 90% when I'm talking. And so we'll say we want 90% of the data to be between our two z-values and 10% of the data to be outside those two z-values. So what we're looking at, and I probably shouldn't have labeled these numbers yet because I don't really know what those numbers should be, but I'm sort of trying to visually, just to get an idea of where I'm looking, think about where on this could I draw a positive and a negative z such that it looks like 90 or so % of the area under that curve is between those two numbers. And there's my guess. Just so that I visually kind of see what I'm looking at. So I want to find this value of z. What is this z right here? So there's negative z and there's positive z. What actually is this z value when we have 90% or so of the data between the two numbers and 10% or so of the data outside of the two numbers? So we've done this where I was given the two z values. So what we said in class is that the area of the curve, the probability between two numbers, is the probability that it's less than z, the probability that it's less than the one on the right-hand side, minus the probability that it is less than negative z. So when we did this in class, I gave you these two numerical values for the z, and I said, what's the probability that this z-score is the whole area? So the probability less than z, that's the whole area here, and the probability that's less than negative z is this little chunk here. So we're going to take the probability of the whole area and then minus this little chunk, and that there equals 0.9030. So we have an equation here. If we knew one of these, we'd know the other one. But it's not super straightforward. Where do I go from here? How do I figure out this without just trial and erroring all 100 or so of these z values to try to figure out which one the right one is? So we're going to think about this a little bit. Let's look for a pattern in the data. Let's just pick a random z-score, and I want to just see the relationship between them. So I'm going to pick one that's easy because it's right on the left-hand side, and it's close. So let's look at z is 0.400. So I'm going to look right here, and I see that the probability of z less than or equal to 0.40 is 0.6554. So P of z less than or equal to 0.40 is 0.6554. 0.4 is clearly not the right z value. If I put 0.4 in here, there's no way that would be 90% of the data. But I'm just kind of looking at this. I'm trying to find an easy to find number on the z chart table so that we can see how these things are related. Okay, so let's go ahead and go to the chart and look at probability that z is less than or equal to negative 0.40. So here's my chart, and here is negative 0.40. So I'm going to follow these two lines down here. Oops, wrong one. And I get 0.3446. So there's something special about the sum of these two numbers. Let's add them together. They add together to be 1. Okay, so, and that should make sense if you think about it. The probability that z is less than or equal to this number plus the probability that z is less than or equal to this number equals 1. Okay, so here's positive z. So it's saying that the probability of this whole area of this curve is that number. And the only part that's missing is this little chunk here. But this little chunk here has the same area as this little chunk here. So the probability that z is to the right of this number is the exact same number as the probability that z is to the left of negative of this number. Does that make sense? So we sort of needed this little realization in order to solve this problem, because now I sort of have a way of thinking about, well, the probability that z is in here and the probability that z is in here are the same number. So I could actually write another equation here, another thing which says that the probability that we're less than z plus the probability that we are greater than negative z okay, so what I wrote here is that the probability that we are less than z, that's this whole thing, plus the probability that we are less than negative z, that's this whole thing, which we just said is equal to this whole thing. Those two numbers add together to be 1. And the reason that this is a helpful thing is that now I have 2 equations and 2 unknowns. So this is something that is in principle solvable. So I'm going to go ahead and solve this equation down here for p of less than z. And then I'll plug that in so that I can get rid of that in this equation, and then I can solve from there. So if I solve this, I get that p of less than z is 1 minus p of less than negative z. We don't need this anymore, so I'm going to cross it off, so this is a little more straightforward. So we'll hop down here next. So I'm just going to go ahead and call this, wow, my notation is kind of clunky here. But I'm just going to stick with it. So probability of less than 0 is 1 minus the probability of less than negative z. So let's take this and plug it in for there. So probability of less than z, that equals this. So let's plug that in. So I'm going to say that 1 minus probability less than negative z. So that was that. So probability of less than z is this equation right here, minus the probability of less than z. Sorry, probability of less than negative z. That whole thing equals 0.9030. Okay, so what did I just do here? I started off with this equation, which we used today in class, which said that the probability to the left of positive z minus the probability to the left of negative z should equal 0.9030. That's what we knew from the beginning. And then, well, this has two unknowns in it, so let's get rid of this. What is the probability that this is less than z? Well, it turns out that the probability this is less than z is equivalent to 1 minus the probability that this is less than negative z. So instead of writing less than z, I'm going to plug in this expression, this relationship for it. And now I have this equation here that only has one thing that I don't know, the probability that it's less than negative z. So let's solve for it. So I'm going to go 1 minus, there's 2 of these, so negative 2 probability that it's less than negative z is 0.9030. And now I can subtract 1 from both sides and have negative 2 times the probability that it's less than negative z is 0.93 minus 0.9030. Oh, sorry, it's 0.9030 minus 1, and that is negative 0.097. Now I'm ready to divide both sides by negative 2. I'll move in this direction. So negative 0.097 divided by negative 2 gives me 0.0485. So I have the probability that it's less than is 0.0485. We're not done yet, but what did we just find? So we just found that the probability for whatever z that we find, that's what we're looking for. We're ultimately looking for this z for which the negative and the positive numbers have 90% of the data between them. And we said that the probability, so the area under the curve less than negative z, whatever negative z ends up being, should be 4.85% of the area under the curve. So here's 4.85%. That is saying that the area under the curve to the left of negative z, that's this area of the curve, right there, that area is 0.0485. That's what we just found. So now we have reduced this to a problem that we've done before. We want to find the z value that corresponds to this number on the table, right? We want the number, the area to the left of this number. So let's look for 0.0485 in the table, and that should be the value of z that we're looking for. So 0.0485, scan through here, and there is my 0.0485. So that corresponds to a z value of negative 1.6, and up here, all the way up 6. So z is negative 1.66. That's negative z. It could also be positive 1.66. And that is my answer. So the z value that corresponds to this situation here, where 90.3% of the area under the curve falls between negative z and z, is z is 1.66 and negative 1.66. And a couple of ways to check this. The first is just does it pass the sniff test? Does the way that I drew this, I tried to draw it as to scale as I could without knowing the answer. So I tried to draw it such that my z's look like the area between the two of them is about 90% of the area under the curve. And so I drew these as numbers between 1 and 2, but that were closer to 2. So that passes at least the sniff check, right? 1.66 is between 1 and 2 and closer to 2. Let's check it though. So for z is, we better find that z of 1.66, right? That's this. Probability of z is 1.66 minus the probability of z is less than negative 1.66. Better equal this number. So can we check? That's what we want to know. Is this right? So if I go, I find my z value of 1.66. I'll move over to the positive side. Here's 1.6. Follow it over to the 6. And I got 0.9515. So that is 0.9515 minus the probability that z is less than or equal to negative 1.66. Negative 1. Negative 1.66 is 0.0485. Do 0.9515 minus 0.0485. And I got 0.903, just like what I wanted, 0.903. All right. So that's a long problem. I think it's hard because you really need to understand what these distributions mean, and what pieces of the curve all fit together to give you the same thing. Okay, so let's recap that a little bit. Usually, let's just use it to do one more example. Okay, so in section 3, which I just want to introduce, we're working with normally distributed variables, and we've actually really been doing this already. So let's give you an example of what I mean. So IQ scores are normally distributed with a mean of 100 and a standard deviation of 16. I want to sketch the shape of the distribution and determine the percentage of people having IQs between 115 and 140. And this is just like the example that we did in the beginning of the class, for how much time it takes students to complete their test. But hopefully we can understand this example a little bit better now. So what we're going to do is we're going to take this and go from there. So let's sketch the shape of the distribution. So here's our distribution. We'll draw a bell-shaped curve to the best that my artwork allows. And The mean is 100, so right here is 100. And the standard deviation is 16. So if I go down here, I look about where this is 2/3 or so as tall as it is up there. That's where I'm going to draw my plus and minus 1 standard deviation lines. So 100 plus 1 standard deviation, that's 116. And 100 minus 1 standard deviation is 100 minus 16, and that's 84. Okay. So we've sketched the shape of the distribution, and now we need to determine the percentage of people having IQs between 115 and 140. So we are looking for, let's go up, we'll do 2 standard deviations here. So if I go 16 more, that'll be 2 standard deviations, so that'll be 132. And I'll do 1 more standard deviation after that to get up to 148. So we are looking for the percent of people that have an IQ between 115, that's all the way down here, and 140, that's all the way up here. So we're looking for the area under that curve. This is a little less straightforward than the example that we did in the beginning of talking about Chapter 6, because these numbers here are not nice, round, even increments of standard deviation like they were for the how long does it take students to complete a test example that we did to start off this chapter. So we need to figure this out, but this is not a z-distribution. A z-distribution is something that has a mean of 1 and a a mean of 0 and a standard deviation of 1. This is something that has a mean of 100 and a standard deviation of 116. So what we are going to do is transform this data into the z-distribution. So here's what I mean by that. A value of 100, that's z equals 0. A value of 116, that's 1 standard deviation above the mean. That's z equals 1. A value of 132, that's z equals 2. What's a value of 115? Remember the formula for the z-score? So if x is 115 minus 100 divided by the standard deviation. I got that is a z-score of 0.9375. And that makes sense, because I expect this z-score to be really close to 1, because 115 is really close to 116. Okay, so now x is 140. The z-score for that is 140 minus 100 divided by 16. And that is a z-score of 2.5. That's a really big z-score, but it makes sense that it's a big z-score because it's all the way out here between 2 and 3 standard deviations as we drew. So here is what I'm looking for, is now, rather than having this data that I have no table for, I can transform this problem. Instead of being between 115 and 140, what I am actually looking for is the area of the curve between z is 0.9375 and z is 2.5. So, find my handy dandy chart. I'm looking for the area to the left of this number, and I'm subtracting it from the area to the left of this number. So I'm looking for 2.5. So go to the positive side. Here's 2.5, and I'm looking for 2.50. That's 0.9938. So minus the z-score of 0.9375, 0.9, and I'm looking for 375, which will round. I only have 2 decimal places here, so I'll go ahead and round that to 0.94, and we will look 0.94, that's 0.8264. And there's my answer. So the percentage of people that have IQs between 115 and 140 is equivalent to the question, which is what percent of z-scores are between 0.93 or are between 0.9375 and 2.5 standard deviations above the mean, and that's about 17% of people. So visually, what have we just done? We have done this. So we can take any distribution that is a bell-shaped distribution and transform it to the standardized normal distribution that we can use our tables with. Okay, so we went through these steps and we said we sketched the normal curve associated with the variable. That was this. We figured out the region of interest. That was this little region here of interest that we were interested in. We used the table to determine the z-scores. And in the end, if it had asked to find the x values that have the z-scores that we found in step 3, we could do that. We didn't have to do that for this problem. So we were looking for the percent of these things. And we can do this for any distribution. So here's a skinny distribution. We could transform that into the z-curve. It has a mean of 3 and a standard deviation of 0.5. So a z-score is x minus the mean divided by the standard deviation. We'll turn it in. This curve turns into something that looks like this. This curve turns into something that looks like this. X minus the mean divided by the standard deviation. This curve can turn into something that looks like this. We do x minus the mean divided by the standard deviation. So why do we standardize? So standardizing the data can shift the data and rescale it so that we can use this standardized normal distribution that we have more information about. So standardizing the scores doesn't change the shape of the distribution. It changes the center by making the mean of the data 0. And it changes the spread by making the standard deviation of 1. Some notable things is that these standardized values have no units. The z-score has no units. This example here, right, we were looking at IQ points, but when we transformed it into z, we were just looking at straight up z-scores. So there was no IQ unit. And z-score is something that is particularly easy to interpret because the value of the z-value tells you the distance of each data value from the mean in the unit of standard deviation. So a z-score of 1 is 1 standard deviation away from the mean. An IQ of 140, I don't know how notable that IQ is, but I certainly know that a z-score, an IQ that corresponds to a z-score of 2.5, is someone who has a really high IQ because their IQ is 2.5 standard deviations above the mean. A negative z-score tells us that that data value is below the mean. A positive z-score tells us that the data value is above the mean. These standardized values have been converted from their original units to the standard statistical unit of standard deviations away from the mean. So that is what the z-score is it tells you how many standard deviations away a number is from the mean. So it allows us to easily compare things that are measured on different scales with different units or from different populations. So the z-score is a really useful thing. Okay, so what's on your quiz on Thursday? So I said that the quiz on Thursday is going to cover Chapter 4 and the beginning of Chapter 6, as well as some things that we've talked about in here. I want to keep in mind that the quiz, I'm hoping, will take everybody 10 minutes or less, which probably means that it'll take about 15 minutes. But it certainly means I'm not going to ask any long problems. There will be a problem. So I have on my current quiz, I have two problems from Chapter 4 that involve this probability of an event, which we'll call event E, is F over N, where F is the number of different ways that you can do something divided by N, which is the total number of possible options. So, for example, we did the example in class of rolling a 1 on a die. So the probability of event E, where E is roll a 1, is 1 divided by 6. There are 6 possible options and only one way to roll a 1. So there is one quick question that is general about what a probability is and how you interpret that number. There is another question that is a probability from a deck of cards. So I think you had a question on your homework. It was question number 4 in the Chapter 4 homework. That would be a good thing to revisit for looking at the probability of events for decks of cards. If you really want to study for it, questions 4, 5, 6, and 7 from the Chapter 4 homework would really well prepare you for this. There is another question that's from a contingency table. So like the Titanic example from class. If you want to know the most relevant homework question to look at would be Chapter 4 homework question number 23. But questions 21, 22, and 23 would all be worth looking at. So that's 3 questions from Chapter 4. And 3 questions from Chapter 6. So there's one question that is asking about basic probabilities of density curves. So what are the basic properties of a density curve? The area under a density curve is 1. A density curve is always greater than 0. It never crosses 0 or hits 0. And the probability of observing any event is the area under the curve in the region of interest. So that would be one question on Chapter 6. The next question will ask you to interpret some probabilities. So it'll say things like it'll give you a probability and say that this is to the left and what is the probability to the right or something like that. So it'll give you a probability and ask you to interpret what that number means. And then the last question will be a z-score question where I give you a z. So the specific format of it will be that I will ask for what is the probability of z less than or equal to some number. And you'll need to look up on the table what that number is. So it won't be a greater than, it won't be between 2 numbers, it won't be some confusing and complicated version of things that we did just now. It'll just be probability of z is less than or equal to some number, and there's 2 of them to look up in the data table. We'll do it as